I'm glad to introduce the next speaker, Georgy C Luke from Indian Institute. Oh, sorry, I don't remember.
Indian Institute
of
Science Education and
Science Education and Research, Tirupati, right? Thank you. And he will tell us about homology and cohomology of topological quandles. Please.
Thank you. Let me thank the organizing committee for giving me this opportunity. So I welcome all kind of suggestions as I'm working towards my PhD thesis. Also, I would like to thank my supervisor, Dr. V. Subhash, and Dr. Mahendra Singh, my RIC member, for steering me through my PhD. And especially I would like to thank Professor Muhammad Alhamdadi for introducing me to the area of topological quandles and suggesting me ideas time to time. Okay, so I will start from the definition of quandles. So by a quandle, many speakers have spoken about this. So it's a set with a binary operation, which I denote by triangle, which satisfies three axioms. The first one is of idempotency, which is x triangle x is x. And then the second axiom is, if you define a map beta y from x to x as x going to x del y, then this map beta y should be invertible for every y in x. The third axiom is of right distributivity, which says x triangle y triangle z is x triangle z triangle y triangle z. We say quandle is a topological quandle. So there is when there is an underlying topological space such that the quandle binary operation xy mapping to x del y is continuous, and the beta y, which we have defined earlier, is a homeomorphism for every y. Most common example which we see everywhere is this n sphere in Rn plus 1. So it's a topological quandle under the operation x triangle y is equal to y scalar multiplied by 2 into inner product of x and y minus x. And moving on to defining a chain complex for constructing our homology. So given x being a topological quandle, then we consider all the collection of singular n simplices. So we take In to be the set of all singular n simplices that's continuous mapped from standard n simplex to x. So this set forms a quandle under the pointwise operation of the quandle operation of underlying set x. So we define sigma n alpha 1 triangle sigma n alpha 2x to be sigma n alpha 1 x triangle sigma n alpha 2x. And now we define the n chain group. So Cnx we define to be the free abelian.
Is it a definition or a property?
No, we are defining the chain complex like this. So so we will get a homology corresponding to topological quandles, analogous to the quandles. So the chain complex we define in this way. So it's a free abelian group generated by all n simplices in the topological quandle X. So we consider the whole collection of continuous map from standard n simplex to X, and then we consider the free abelian group generated by all those maps. So that's our CNX. And then the boundary map we define similar to that of quandle homology. So del n of an n simplex, n singular simplex. So the catch here is these are singular simplexes. So del n of so the singular simplex we denote sigma x1 up to xn plus 1. So it's a singular simplex. So the vertices of the standard n simplex maps to elements in X. So sigma x1 up to xn plus 1 is the simplex such that the vertex ei of standard n simplex is mapped to xi plus 1. So the boundary of that sigma is summation I running from 2 to n plus 1 minus 1 power I, the ith phase of the simplex sigma minus ith phase of the simplex triangle with the simplex, which I call to be degenerate simplex of sigma. So it's we denote it by sigma xi I minus 1 times then xi plus 1 up to xn plus 1. So we define this how to see this degenerate sigma. So this n minus 1 simplex, we define it in the following way. So it's composition of two maps, I from delta n minus 1 to delta n, and then the maps, the n simplex sigma from delta n to x. So I is mapped in the following way. So if ej bar, the set ej bar from j running to 0 to n minus 1 is the set of vertices of standard n minus 1 simplex, and set ej, it's the set of vertices of standard n simplex, then we map I in this following way. So I takes summation, the linear combination of tj ej bars running from 0 to n minus 1 to summation k is equal to 0 to I minus 2 tk ei minus 1 plus summation j running from I minus 1 to n minus 1 tj ej plus 1. So this this degenerate simplex sigma is spanned by the elements xi from xi to xn plus 1. And now on we denote the new this m plus 1 simplex sigma x1 up to xm plus 1 triangle sigma y1 up to ym plus 1 in following way. So it's just for the notation, for easy notation, we write it like this. So the theorem is in fact this will be a chain complex. So the composition del n minus 1 as a map from cnx to cn minus 2x will be 0. The proof is like this. So delta, so we by definition we consider del n of sigma and then we take del n minus 1. So again we use the linearity of del n minus 1. So there are two components in the summation part. So we take a del n minus 1 of each these components. So we will get 8 such components, eight such summations. So first 4 corresponding to the first component of del n sigma, and the rest 4 corresponding to the second component of that is this part of del n sigma. So we can see that each of these terms pairwise cancel each other. So for example, this so it's basically using the property that the set of simplices in, which we have defined earlier, it's forming a quandle, and then we using the quandle axioms to show that these cancel each other. So out of these 8 terms, pairwise, each of these things will cancel each other. So del square is 0 map. And now what we do is that we again define chain complex similarly, like so I use another notation, C bar Rn of x. So similar to we constructed the Reich homology of quandle. So C bar Rn of x is defined to be Cnx modulo a relation tilde So this relation tilde is defined followingly. So two n-simplex sigma and beta are related if sigma ei is equal to beta ei for I running from 0 to n. So which means the image of vertices of the standard n-simplex is same by the mapping of sigma and beta. Similarly, we define the degenerate homology of quandles. We can define C bar dnx to be the subgroup of C bar Rnx generated by those n-simplexes sigmas with xi equal to xi plus 1 for I belonging to the set 1 to n. For n greater than 1 and elsewhere it's 0. And then the boundary operator is the restriction mark. And similarly, we define C bar Q of n of x to be the quotient of C bar Rnx modulo C bar dnx. And the boundary operator here will be the induced operator. Similarly, we can define the cochain group. So C bar n W of xa, the nth cochain group with coefficient group A, we define it to be the group of homomorphisms from the nth chain group of X to A. So note that for W could be R, D, or Q here. So for each chain groups, we whether it's C bar R or C bar D or C bar Q, we define the cochain groups as homomorphisms from the chain group to the coefficient group. And the boundary map delta n we define as delta n phi to be del n plus 1 phi. So where phi belongs to the phi is a n chain. And we use the notation, this notation h bar wn of xa to be the for the nth homology group, and h bar n w of xa for the nth cohomology group, for where w varies are d or q. Yeah, and our theorem, an important theorem is this. So if X is a topological quandle and the underlying topology is indiscrete topology, then the whatever homology group we are constructing, that H bar and W of X is isomorphic. This is isomorphic to Hn plus 1 W of X. So note that this Hn plus 1 W of X is our usual quandle homology groups. So n plus 1 is the n plus 1 quandle homology group. So when topological quandle is with indiscrete topology, this thing holds. So I will just explain the proof very briefly. So if F is a if F is a cochain, then we define a map psi n from C bar and W of X to Cn plus 1 W of X. So Cn plus 1 W of X is our usual quandle homology chain complex. So this under this map, psi n of F is defined to be a map F hash. So F hash, we define it to be F hash of x1 up to xn plus 1 to be F evaluated on the n simplex sigma. So this is how we define it. So there is a one-to-one correspondence between the cochain groups. And then we can see that actually this diagram commutes. So it turns out that delta n plus 1 F hash is del n F hash, delta n F hash. So it's coming from this computation. So it's not hard, it's just using the linear property of F. And then applying the definition of del n and del n plus 1. That's all. So the characteristic function, if sigma is a generator of C bar Qn, then a characteristic function we define chi sigma, the chi sigma x1 up to xn plus 1 as a map from C bar Qn to Z in the following way. So chi sigma x1 up to xn plus 1 of sigma y1 up to yn plus 1 is 1 if both the symbols are the same. It's 0 otherwise. So we compute the homology and cohomology groups for some topological quandle. So if X is a set 1, 2, 3, and the quandle operation table is this, and if the topology is such that the non-trivial open sets are singleton 1 and the set 2, 3, so we compute for such space we compute the zeroth homology, cohomology, and similarly for the first homology and cohomology groups we compute. So for that we go by the usual procedure. So the C bar Q0X is the free abelian group generated by the constant symbols which maps to element 1, 2, and 3. So it's Z3, and then C bar Q1 of X is the free abelian group generated by non-degenerate paths. But under this topology, so the path components are singleton 1 and the set 2, 3. So the degenerate paths are possible. The only degenerate paths could be sigma 2, 3 and sigma 3, 2. And similarly, C bar Q2 of X. So the two symbols, it's again lie inside some path component. So the non-degenerate two symbols could be sigma 2, 3, 2 and sigma 3, 2, 3. And then we compute the boundary maps. Del 1 is 0 map here, so is del 2. So the corresponding homology groups will be just the chain groups. So it follows. And similarly for computing the cohomology groups, so if F is a first cochain, then F will be of the form linear combination of the generate characteristic function. So F is C23 chi sigma 23 plus C32 chi sigma 32. So these C23 and C32 are the constants. So in this case also delta 1 is a 0 map. So it's because the boundary map, this del 2 is 0 map. So also del 0 is also a 0 map here, since delta 0 is 0 map, since del 1 is a 0 map here. So again Z bar 0 Q of X is C bar 0 QX and B bar 1 Q of X is 0. So again our so these elements will so the theorem follows. So it's again the same. H bar 1 Q is just C bar 1 Q of X. So now we consider YB topological quandle, but with indiscrete topology. So this we have already seen by the theorem before. In this case, H bar Q1Y will be isomorphic to H of sorry, I think there is a typo. This is actually we want to compute the cohomology group. So by notation, it should be H bar 1 QY. So in this case, H bar 1 qi will be isomorphic to h of 2 q of y, where h2 qy corresponds to the second cohomology group of quandles, where y is the quandle, the underlying quandle. The quandle is same for both these two examples, but the topology is different. So any cochain will be of this form: summation Cij's chi sigma ij's I not equal to j, and ij belongs to y. And then the fact that it's a cocycle gives the condition that CPR minus CP del QR minus CPQ plus CP del R comma Q del R is 0, where this three tuple PQR is a degenerate, non-degenerate three tuple. So this actually computing these things gives the condition, these two conditions, C23 and C32 should be 0, and C12 should be equal to C13. So any cocycle can be written in this form. It's generated by three elements, and when we compute del 1 is non-zero for evaluating over sigma 31 and sigma 21. So del 1 sigma 31 is sigma 3 minus sigma 2. So from that we get that delta chi sigma 1 is 0, delta chi sigma 2 is chi sigma 21 minus chi sigma 31, and delta chi sigma 3 is minus del chi sigma 2. So h bar 1 qy is generated by two generators. So it's isomorphic to Z2. So we just use a lemma. So if X is a topological quandle and X alpha are the path components, then each X alpha is a topological subquandle. So the proof is easy. So since beta y is a homomorphism, beta y X alpha should be path connected. So if we take X and Y in same path component X alpha, then beta y of y and beta y of X should be in same component. But beta y of y is y, and it belongs to X alpha. So beta y of X, which is X del y, should also be in X alpha. So X alpha is closed under the quandle operation, and the other properties of topological quandle follows. And for defining, so our colorings are a bit different from that of quandles, quandle coloring. So here, given a topological quandle, we consider all path components of X alphas, and then we consider the colorings over a diagram of a node via those components X alphas. So now phi be a one cocycle, phi belongs to Z bar 1 q of X, and then for a crossing colored by for a diagram colored by some X alpha, and we call that coloring C alpha. And for such a coloring at a crossing theta, we define the weight B theta C alpha as follows. So if the over arc is R and the under arcs are R1 and R2 such that the direction of the normal vector of R points from R1 to R2, then we color, then if R is colored Y and R1 is colored X, then for this crossing we define the weight to be phi of beta of xy. And if it's a negative crossing, we take it to be phi of beta xy inverse. For the state sum invariant for node diagram, we define it to be the sum of products of all crossings of node diagram colored by path components X alphas of X, and we denote it by capital phi of k. So the important theorem is that if phi is in Z bar 1 q of xi, then the state sum invariant associated to phi is in fact a not invariant. So for calculating purpose, we consider the characteristic functions multiplicatively for calculating the state sum invariant. So chi sigma of xy of sigma f ab, we define it to be t, and the coefficient group we take it to be cyclic group generated by t. So chi sigma of xy of sigma of ab is t. The parts are the same. It's 1 otherwise. So as an example, so I consider two Hoflings, but with different orientations. So we have computed two examples with same quandle structure, but with two different topologies. One was indiscrete, and other was where non-trivial open sets are singleton 1 and the set 2, 3. So under this, when we consider that quandle with 3 elements, 1, 2, and 3, so there are actually 5 colorings. So here, 3 out of 5 colorings, 3 of them are trivial colorings, and then the rest 2 are non-trivial colorings. So A could be 2 and B could be 3, and A could be 3 and B could be 2. But if we use the phi belongs to Z bar 1 QY, which was the quandle with indiscrete topology. So in that case, the calculating state sum invariant is equivalent to calculating with the quandle cocycle corresponding to Y. But in that case, it turns to be the state sum invariant is trivial. But in fact, if we choose the topological quandle with non-trivial, non-indiscrete topology, which we have seen, which we have taken as X, and if we choose phi is equal to chi sigma 2, 3, then it turns out to be the state sum invariant is 3 plus 2t for the first Hofling here, and for 3 plus 2t inverse here. So 3 comes from the 3 trivial colorings, and t comes from the contribution for the non-trivial colorings. That's when A is 2 and B is 3, or vice versa. So, and for here, since the crossings are negative, so it will become T inverse. Yeah, so it follows. So that's all for my presentation. Thank you all for listening to me. Thank you.
Thank you. Are there any questions or comments?
I have one question.
Yeah, sure.
Thank you for first. Thank you for interesting talk. I have a question. For topological quandle, there is a well-known things. I mean, coming from Lie groups, right? For them, is there any calculation for known the topological quandles?
I am not familiar with the connection between Lie groups and topological quandles. I haven't. It didn't came to my notice so far. Sorry, like.
Okay.
I'm sorry.
Thank you.
Some more questions or comments?
So may I ask one question?
Yes, sir. Yes, sir.
Yeah, you're welcome.
Yeah, thanks, Georgie, for the talk. Maybe you already said and I missed it. So if you have a topological quandle, and so on one hand, you can talk about the usual quandle cohomology of that, viewing it as a discrete space. And then
in discrete space.
Discrete. And on the other hand, you have your cohomology, taking topology into consideration. So I'm wondering, is there a general relation between them? Have you?
Yeah, I have stated that. So,
but you said some indiscrete. What does indiscrete mean here?
So I'm saying, given a quandle, we can always give it a topological quandle structure by giving it the indiscrete topology.
Indiscrete means only open sets are the
No, no. What I meant is all subsets are open sets.
That's discrete.
Huh?
That's the discrete topology.
Yeah,
right?
yeah.
So throughout you have written indiscrete, so I was a little confused.
1 minute. Yeah, it's indiscrete only. So what you have said is correct. The only open sets are MD set and the whole space. So any map we take, it turns out to be continuous. That was the idea behind that. So when so for indiscrete setting, the maps which we have, the symbols which we have defined are maps from standard n symbols to X. So
Yes.
it turns out that when we give it the indiscrete topology structure to check the continuity, so we have to check the inverse image of open sets are open. So whether it's empty or whole space, it turns out to be open.
So you cover the usual quandle cohomology.
Yeah, we get the usual quandle cohomology and homology in that case.
But I'm asking, if you have a topological quandle with a non-trivial topology, forget non-discrete and also not the discrete one.
Yeah.
So then you have two cohomologies for that. Is there a general relation? You can talk about the usual quandle cohomology and as well as your cohomology. So,
yeah, there is always a group homomorphism between the whatever given any topological quandle and considering this topological quandle homology, there is always a homomorphism between the usual quandle homology groups. But just it's that the one order is different, like H bar NX will be, there is a group homomorphism from H bar NX to Hn plus 1 X, where Hn plus 1 is n plus 1 quandle homology groups. There is a homomorphism. But when we give, when we consider the indiscrete topology case, this homomorphism is actually an isomorphism.
oh, I see. Okay.
That's what I.
Thank you.
Thank you, sir.
So if there are no more questions, then let us thank the speaker again